Hello, welcome. This is Algebra 2, Chapter 7, Section 1. We're on page 3 of the notes. It's a long story problem that's mostly a lot of writing, not necessarily a whole lot of thinking. But there's a key thing that happens here, so key formula that comes up. So it's worth our time. Buffalo. All right. In the last 12 years, an initial population of 38 buffalo in a state park grew by about 7% per year. Be clear, this is the population that's growing by 7%. This is not intended to indicate that the buffalo themselves are each growing 7%. First, we're going to do part A. Write an exponential growth model giving the number n of buffalo after t years. And then how many buffalo were in the park after 7 years. Well, let's go back to that here. Boom, part A. The initial amount is A equals 38 because they said there were originally 38 buffalo in the state park. And the percent increase is R equals 0.07. Now, of course, they said 7%, so to be honest, they probably shouldn't have used the word percent in the sentence there, but what are you going to do? So, the exponential growth model is, and this is a thing to know, this is very similar to something else that's going to come up on the very end of the page, but n equals a times 1 plus r to the t. Now, I think hopefully explanatory, but maybe not. N is the number you have. Maybe number at the end, because A is the number at the beginning, so beginning number. R is the growth rate. This only works if things grow the same percentage every year, but it has to be written as a decimal, not as the percent itself. So boom, it has to be written as a decimal. And t is the time. Pretty much means years. Okay, so in this case, though, we have values to plug in, so we can go ahead and calculate a number out. The initial number was 38. We have 1 plus 0.07. And then the question was after 7 years? Oh, no, just after t years, excuse me. So to the t. And so it's 38 times, and then 1 plus 0.07 is 1.07. That's quite possibly the least exciting thing anybody's told you today. So it's 38 times 1.07 to the t. And then here's the part that I had mistaken it for. They said at the end they do want to know what happens after 7 years. And after 7 years, you have 38 times 1.07 to the 7. And that's about 61 buffalo. Now, of course, that's not exactly 61 buffalo. You might have an extra tail or be missing a hoof, but you go to the nearest whole number because that's the only thing that really makes sense here. All right, that's part A. Now let's look back a little bit and see we have to do part B here. It says graph the model. You know what? We're going to graph it because they tell us to graph it. The graph is, well, you'll see, unexciting. But there is value in figuring out what's going on here. Okay, they want us to treat this graph like it's an exponential growth model. And the reason why they want us to do that is because, well, it is an exponential growth model. So use the point when x is 0, or in this case when t is 0. If you plug in 0, you get 1.07 to the 0, which is 1 times 38 is 38. So you have the point 0 comma 38. Boom, there's a dot, and 1 comma, and if you plug in 1, and 1.07 to the 1 is 1.07, times 1 is 40.66. Of course, on the scale, there's no way any person could graph exactly 40.66, so you do your best, you make a dot, tiny bit above 40, and you call it good. And then it says, plot a few other points, like, I don't know, that's really unhelpful. So I was thinking, to do that, we should maybe just go ahead and do some numbers that are a little bit farther away. So like when when t is 5. And when t is 5, if you substitute it in, you get about 53.3-ish. So you have 5, comma, 53.3-ish, just a bit above 50. Boom. And then maybe when t is 9, 69.8-ish. So I'll write 69.8. Of course, we know that means realistically we're looking at 70. So when t is 9, we're talking about 70, which is there. And then we're supposed to connect these with a smooth curve. This is not meant to be a line. It's actually a very, very slow-growing exponential model. That is a graph that's supposed to have the same shape throughout. My drawing is imprecise. Part of it is because I fail at drawing. Excuse me for that. And part of it's just because the tools aren't very good. But it says, using the graph, you can estimate the number of buffalo was 53 after about, and the answer is, of course, that it took 5 years, and we know that, well, we know that because when we plugged in 5, we got about 53 buffalo. Realistically, doing this part to find when you're going to have 53 buffalo or a certain number of something, the graph is the wrong tool for that. So, but hey, we made a graph. It's an exponential graph. Yay us. Now, let's go ahead and look at the box on the bottom of page 3, though. This compound interest formula. This is a big deal right here. This is a definite big deal. Boom, boom, double underlined in red. Consider an initial principal P. Now, principal means initial amount. That's why they said initial principal, but I'm going to write it again because that is a big deal. What's the initial amount? Invested in an account that pays interest at an annual rate R, and see here they did kindly say expressed as a decimal, compounded n times per year. Now that means compounded is how often they give you the interest. We'll talk about that in class a little bit. And then the amount A after t years. So A in this case is the final amount. After t years is given by, and then here's the formula. It's in your book. It's a big deal. P, parentheses, 1 plus R over N, N parentheses, to the NT. This is a supremely important formula from Algebra 2. Maybe it's kind of like you learned the quadratic formula in Algebra 1. It's a big deal. So it's boxed, it's double underlined on the topic. It's got notes about what the different variables mean. This is a thing. Anyway, thank you for watching. On page 4, we will use this new formula in an example and a couple of checkpoints.